Okay, this is what I plan to do in class on Monday, November the 30th, for reviewing for our Unit 4 exam. We have all these equations that we have learned, and they are on your green sheet. But essentially, we know that work is equal to force times distance times cosine theta. Theta is the angle between the force vector and the displacement vector. We also know, and we should know, this is something I should know, is that the net work is equal to the change in kinetic energy. That's always true. That is not on your equation sheet. We know that the change in energy is equal to work, and that is on your equation sheet. And that when work done by force of friction equals 0 and force of applied equals 0, we know that energy is conserved, right? Because delta E will equal 0, okay? So we have set our equations up such that mechanical energy initial equals mechanical energy final. That means final minus initial equals 0. Now, if I had work done by friction, I can easily add it. Plus work equals mechanical energy final. So all of that came from this equation, okay? So we can use the conservation of energy approach and add in the work done by force of friction and force of applied to solve some things, okay? The other thing we know is that power is equal to how much work I've done versus over time. And I can substitute the definition of work into that over time. D over T will end up being the average velocity times cosine theta. Okay, so that's important. I think I have one question related to that, and this is not on your green sheet, what I've highlighted in yellow. In fact, what's on your green sheet is power equals change in energy over time. Well, what's change in energy? It's equal to work. So it's work over time, okay? Equals work over time, which equals the force times the average velocity times cosine theta, assuming that force is not parallel to the surface. A couple other things that we have learned. We know that force of a spring is equal to the absolute, so the absolute value of the force of the spring is equal to the distance it's been stretched times the K constant. Those force of the spring and the distance it's stretched are always opposite. We also learned the equations for kinetic energy, potential energy due to gravity, and potential energy due to a spring. Okay, those are also on your green sheet. Okay, so a couple things I want to talk about, and I'll talk about this force of a spring situation. So if I stretch the spring this way, and this is x equals 0, then x was positive. Actually, let's do it a different way. Let's assume this is x equals 0. This is x, some positive number, I don't know. We'll call that maybe 2 centimeters. The force of the spring, I'm having to pull that with my force applied. Which direction is the force of the spring pulling? Trying to get back to equilibrium. So the displacement was to the right, the force of the spring is to the left. So they're always opposite in direction. Okay, now let's just talk a little bit about system definition, mechanical energy. I want to talk about and plan to talk about this whole approach right here when change in energy is equal to 0 and how the system being defined makes a big difference, okay? So let's assume I have some block, I've dropped it, and it's falling to the ground. And let's assume I define my system as the system is earth block, okay? The only forces that are happening are the internal forces between the gravitational attraction between the block and the earth. So there is no outside forces. So the change in energy is equal to 0. And we know that energy initial has to equal energy final. And it essentially will transfer energy back and forth between kinetic energy and potential energy due to gravity. So there's no change. This total energy, this mechanical energy total. So if I added up the energy at any particular point, that number will be constant the entire time. Kinetic energy is going to change as it falls, but potential energy is decreasing. So they convert back and forth between one another. And I have defined my system as an earth block system. Now, what if I did the exact same situation, but I define my system? So let's just draw, the system is the block. Now, there is an outside force. There is something being done by an outside force. And that happens to be, if this is the system, what's the outside force? Happens to be force of gravity. So what kind of energy is going to change? Well, I don't have potential energy due to gravity anymore because I have no earth involved. So I'm going to have a change in kinetic energy that is related to the work that is being done by force of gravity, since now force of gravity is considered an outside force, and it's increasing because the kinetic energy is decreasing or increasing, excuse me, because my displacement is downward, and that's cosine of 0. Cosine of 0 is 1. So I am gaining kinetic energy as I fall due to the work that's being done by force of gravity when I define my system as only the block. Okay, let's do one other situation. What happens if I have a person who lowers the block at a constant speed? So they put their hand under the block, there's a force applied, there's a force of gravity acting on it, and I lower it at a constant speed. The net work being done is 0, okay, on the block, right? Because the force applied is going to equal the force of gravity if I'm decreasing the height by a constant speed. But what if I define that? What do I want to know about the change in energy of the block Earth system in this scenario? Exactly the same thing. So now I define it as the block Earth. Well, your hand's reaching into the block Earth as an outside force. So this is considered an outside force. That force of gravity is now inside. So now what's happening is the energy initial plus the work done by force applied, which is my hand, it has to equal the energy final. And since I now have the Earth as part of my system, I have potential energy due to gravity. Well, we already said the kinetic energy is not changing because it was at a constant speed. So we can kind of think about that going away because they're equaling one another. They'll cancel on both sides of that equation. However, the potential energy due to gravity, if I'm lowering it, is decreasing. And why is that decreasing? Well, it's decreasing because the force applied is upwards and I'm slowly dropping it downward, and that force applied is doing a negative work because the cosine between the force applied direction and the distance is that angle is 180, so that is negative work. So there's some kind of, so you have to be very careful about what the system is being defined as, and also what the question is asking. So be very, very careful about the question. Okay. Let's see. Pendulums. We talked about pendulums on a day. I need to talk about it again. There is a pendulum problem on this. There will be probably on the AP exam as well. Pendulums conserve energy as well. So if I have some initial height and I drop down to maybe that's considered my 0 line. Energy is conserved in the situation, so its potential energy due to gravity initial will equal that kinetic energy final if I drop it from rest, because its kinetic energy initial, that would be equal to 0, and potential energy due to gravity final would also be equal to 0. So I'm converting back and forth between potential energy due to gravity and kinetic energy if I assume air resistance is 0. So it's hopefully a straightforward height problem where we're trying to use conservation of energy. Change in energy is equal to 0. So if I were to draw, my total mechanical energy would be constant. Potential energy would be increasing and decreasing and increasing and decreasing depending on, let's see, what would I want to do this for if it was versus height? Actually, I'm not gonna, there's not a graph on this one, but it just depends on what they're asking for. If it's versus time, it's not linear. If it's versus height, it is linear. Okay, let's keep going. Let's see. The next one is that I wanted to go over is a situation where I know if I have an object with some initial velocity, maybe it's 5 meters per second, comes to some stop, right? And I want to know how much, let's say, work was done by friction. Well, this is on the same level, right? There's no change in height. So the change in energy has to equal work, or energy initial plus work. What's doing work? Friction equals energy final. We know that this is always going to subtract energy, so we can because I know it's going to be cosine of 180, so we're going to subtract that. I can calculate some things. So I know that it's going to have kinetic energy initial, no energy final, and maybe I might be looking for the force of friction or mu k, but I could very easily see a problem like that on the test tomorrow where I have to apply change in energy is equal to work, or change, in this case, kinetic energy is equal to work done by friction. That's the only kind of energy that we're talking about. What's doing work? Work done by friction. What if I had it on an incline? Now all of a sudden, maybe it's sitting here at 0 and some velocity, I don't know, final, we don't know what it is. Maybe we want to know how much kinetic energy is here. Question mark. Well, now I have an elevation change, right? I know that the energy initial is equal to the energy final if there's no work done by friction. What kind of energy initial do I have? Potential energy due to gravity plus kinetic energy initial has got to equal potential energy due to gravity final plus kinetic energy final. This is 0, this is 0, and I can solve from things. What if there's friction involved? Well, energy initial plus work done by friction. I know that that's going to end up being negative, so I'm going to subtract the work done by friction. So then I just don't have to worry about that. Cosine 180 is equal to energy final. And I might have to solve for force of friction or mu k or kinetic energy at the bottom. So depending on whether or not there's friction or not, I might have to apply it on a horizontal surface, or I'd have to apply it on a plane, okay? Okay, let's talk about some spring problems. What if I have a spring and I tell you that I'm holding the spring with a force of 10 newtons, and I tell you K is equal to 600 Newton meters, and I want to know how much potential energy due to a spring is sitting there, which is mu s, which is the equation 1k x squared. I didn't give you x though, but I told you how much force is sitting there holding it. Well, the force of the spring is in the opposite direction, and I know that force of the spring is equal to kx. If I know how much force I'm holding that at, I know what the force of the spring is, I know k, I can calculate x, and then I can come in here and calculate the potential energy due to the spring that's currently sitting there. What if I tell you that the potential energy due to the spring is 10 joules, and I want to know how much the maximum speed an object can have if it is sitting on a compressed spring with all that energy? Well, then energy initial, which is the spring initial, has to equal the energy final, right? So maybe this is x equals 0. The energy final is just kinetic energy because there's no more spring compression, and I can solve for the velocity of the object if I know the K constant and the amount that the spring was compressed. Okay, what if I give you a graph of force of a spring versus time? I'm sorry, not time. Versus distance compressed. So the X value. So this is in meters, this is in newtons. What can we determine? So the area is the work that was done to pull that spring or compress that spring, depending on what it is. And the slope is the K constant. So don't forget your graphs. Okay. Okay. There is one problem. Oh, let me do one more thing. I have an object and I am moving in this direction. If I have an object, I'm moving in this direction. There's the velocity. And I come along and put a force at that instant. How much does the velocity change at that nanosecond? Well, that force does zero work. So there's no change in velocity for a nanosecond. Okay, now it's going to start to accelerate and change the velocity and pull the velocity in that direction because it's going to accelerate in that direction. But for 1 nanosecond, it does not change the velocity. It will start to change the direction, but it will not change the velocity. Once that angle is no longer 90 degrees, then the velocity will change. Okay. The other thing is, depending on whether or not that force, you've got to pay attention to your cosines, I guess is what I'm trying to say. If you want to know which one increases the speed more, and the forces are the same, you will just look at the angles. Okay, all you will do is evaluate the angles. Which one causes positive work, which one causes the largest positive work, and which one causes negative work. So depending on what they're asking, pay attention to the question, of course, but if it's related to, let's say, a speed change or a work, especially a speed change, which is determined by work is equal to the change in kinetic energy, then you will look only at the cosines of those forces. Okay. If the network is zero, equals zero, the change in kinetic energy has to equal zero, right? Okay. Pay attention to words. Okay. Last thing, I would review your graphs on kinetic energy and potential energy due to gravity. If I have a spring and I want to know kinetic energy versus distance, I personally find that potential energy versus, we know that they're going to convert back and forth, but what I want to say is that I find it easier. So these are maybe X values, and maybe at X equals 0. So this is X equals 0. This is maybe -1, -2, -3. Potential energy due to the spring is large. Kinetic energy is 0. And then potential energy of the spring is 1/2 kx squared. And so originally I'm at 3, then I'm at 2, then I'm at 1. I have to square it. So 9, 4, 1. This goes 5, this goes. So it changes quickly until it reaches x0. And then kinetic energy does the exact opposite. Okay, that's a terrible graph, but nevertheless. And then what happens? If it's frictionless, it's constant. If there is friction, that is proportional to distance. And so review those. I had several of those graphs. Review those, please, to know the shape of your curves. Okay, that's what I got for you. That's what we're going over in class. The other thing I would suggest is reviewing your worksheets. Have a good day.